My name is Rachel Kurchin. I'm a postdoc at Carnegie Mellon University, and I'm the lead developer of Chemellia, a machine learning ecosystem specifically designed for learning on systems made of atoms. So these could be from the fields of chemistry, materials science, physics, and many number of engineering applications. And this type of application has really taken off in recent years. You've likely heard of at least one of these software packages designed for exactly this purpose. And there's also in the commercial space a variety of companies that are really starting to make use of these techniques. Now, what types of tasks are these software packages designed for, or are these companies undertaking? Well, I won't claim that this is an exhaustive list, but many of the machine learning tasks in atomic systems that I have seen fall into one of the following three categories. So first would be to surrogatize expensive first principle simulations. These could be things like density functional theory or other quantum chemistry codes. So the idea here is that we run this code a bunch of times, typically generate a training set, and then after that, completely replace the use of that code with a much cheaper to evaluate machine learned surrogate. We could also use it to accelerate the convergence of those models. So in this case, we're still using the first principles model, but we use machine learning to, for example, improve the initial guess, or perhaps make the optimization algorithm used by that model much smarter, generally aimed at reducing the number of steps required for that model to converge. And finally, a lot of folks are also interested in improved potentials or equivalently force fields for particle-based simulations. All of these applications really require great computational performance, oftentimes interoperability between different systems, nice composability between different functions, oftentimes easy automatic differentiability is another plus. And so Julia is extremely well suited for these types of applications, as I probably don't have to convince this audience. However, there is no comprehensive ecosystem for it in the Julia language, unlike an abundance of options, generally Python-based, that I showed a couple slides ago. So the goal of Chemellia is to be that ecosystem. We're trying to build it. So I won't actually bore you with too many more slides. I want to be able to jump into some hands-on demos, but I'll first talk a little bit about the overall structure of the package and primarily this featurization package that it's based on, some aspects of the design philosophy, and then we'll jump into some great demos. So the core package of Chemellia is ChemistryFeaturization, and this is the package that we use to read in structure files. These are just a couple of examples of the file formats that we support currently via the atomic simulation environment's IO module via PyCall. This allows us to build an atoms object. So this is the representation of the structure of that system in whatever format the machine learning model wants to take in. So that could be, for example, a graph, and that's the AtomGraph type. Then we can also define a featurization scheme. So this is what do we actually do to encode the features that we're interested in of that object to feed into that model. And the core ingredients of the scheme are what are called feature descriptors. So these are individual pieces of information that we might want to encode. So they could be features of individual elements. That's an element feature descriptor, which we'll show in a demo. But we might also have features of pairs of atoms or some features that depend on a local environment. And the idea here is to have these reusable pieces that might be part of many different featurizations. So those act on the structure object, on the atoms object, to create encoded features, which can then be attached to it and create that featurized atoms object, which will then be the input to the actual model. So I'll talk a little bit about the design philosophy of this package. First and foremost, we want it to be modular, customizable, and very easy to extend. So the modularity comes from those feature descriptors. A featurization scheme itself will often be one-to-one or close to one-to-one with a type of model, but many times there will be individual feature descriptors that could be used by many different featurizations. So many different featurizations might want to know, for example, the atomic mass of a given element, even though it might be encoded in a slightly different way by different featurization schemes. And that gets to this customizability. So you can choose how that thing is decoded or how encoded and decoded, how many, if you're going to use some sort of one-hot representation, how many bins are you dividing it into? Are those bins linearly or logarithmically spaced? All of these options are very transparent to the user and very easy to customize. And similarly, it's easy to extend. If you have some feature that isn't currently supported and you want to add it, you can create a new feature descriptor. And whether that's just creating providing data that needs to be looked up in a table or something more involved, we hope that the API is transparent enough that users are able to easily add more such features. We want it also to always be decodable. So this comes down to the fact that the featurization scheme and the feature descriptors are actually still attached to that featurized atoms object, not just the final encoded features. So I'm sure this has never happened to any of you, But imagine you had built a bunch of structure representations, featurized them, serialized them to be able to quickly move them around and read in somewhere else, and then lost track of the script that you used to actually do that featurization. Well, in many current ecosystems, you might just be up a creek. You might not know what exact information is encoded because it might just be a bunch of one-hot vectors. But with this system, you're actually able to store that information and query it and say, okay, how did I encode this? Can I actually just decode it and see, with what resolution did I actually encode this feature? So we try as much as possible to maintain that decodability. And then finally, we hope that the system can be universal. I've noticed, and perhaps you have too, that many of the machine learning applications in the broad atomic system space end up kind of bifurcating into folks that are more focused on organic, molecular type systems versus inorganic, more crystalline systems. And we really hope that this package can be a step towards uniting those communities and allowing them to learn from each other and use, to the extent that they're applicable, things like feature descriptors or even featurization schemes from one and the other. One example of something that facilitates this is a function called encodable elements. So every feature descriptor type must dispatch this function, and it simply tells you, okay, what elements are valid to encode this feature on. So many organic systems have a relatively small set of elements for which the features are applicable, whereas inorganic systems inorganic folks tend to be interested in a broader range of atoms. But this allows you can very easily tell when can I pull from one versus the other if I want to create some sort of hybrid featurization. So that's enough for the slide deck. I want to turn it over to some demos. So first, I will be giving a demo of that atom graph type. How do we construct them? How do we work with them, visualize them, etc.
Okay, here I am over in VS Code, and we're gonna see how some atom graphs work. So we can start off by building one what I call kind of by hand. So we'll manually specify an adjacency matrix. So this is just for a little triangle. Node 1 is connected to nodes 2 and 3. Node 2 is connected to nodes 1 and 3, etc. So let's just make a little triangle of carbon atoms. This is obviously not a particularly physical molecule, but it gives us a sense of how the whole thing works. We can visualize it like so. Oops, that's not the right one. Spoiler alert. So as expected, we get a nice little triangle. Note the thicknesses of the lines correspond to the weights, which in this case are all the same, but we'll see an example momentarily where they are different. So, this is all great and it's nice for an interactive demo, but in practice, you're generally going to want to build graphs from a file, perhaps many graphs from a file. So I have here downloaded from materials project the structure for tungsten disulfide, which is a common two-dimensional material. And we can see that it will happily build a graph from that CIF file there, and we can visualize that guy. And so we see something interesting, which is that it's actually a disconnected graph. We have these two separate triangles, which we can rationalize a little better if we open up Vesta and look at the actual structure. So I've repeated the unit cell here twice in both X and Y, and you can see that you do in fact have these kind of two disconnected layers. Why there are only two sulfurs connected to each tungsten becomes a little more clear if we actually turn off the automatic bond visualization. And then we'll see that in fact within the unit cell, actually let's turn off the repeats as well, I meant to do that. We can see in fact that there are actually only two sulfur atoms within the unit cell, the other ones are periodic images. So what I've done here has built the graph with all of the defaults, which are pulled from the original CGCNN.py, and this involves basically just setting a cutoff radius and a maximum number of allowed neighbors. But perhaps a little bit more physical way to do things is if we build the graph by using a Voronoi tessellation. So in this approach, we make the Voronoi tessellation of the structure, and any atom that shares a face with another atom become neighbors of each other. And so the graph is built that way. And we'll see actually that we get a qualitatively different looking graph in that there actually are connections now. So you get these sort of connections between this sulfur atom and this one, as well as this one and this one across the unit cell boundary. This all becomes another way we can see the disconnectedness here. We can actually query the graph itself. So if we look at the original one, we can see the weights, which are stored as a sparse array. This becomes even clearer to see that it's disconnected if we actually index into it in a different order, in this way you can see that in that first one you have these two disconnected ones. And if we do the same thing for this one, we see they're still more densely connected within those two separate areas, but we in fact do have some connections between the two, consistent with what we see in the visualization here. And again, here you can see the weights being substantially different from each other. Note also that those weights by default will normalize to 1. You can turn that flag off if you want, and it'll just come out to whatever raw number comes out, but it's not necessarily going to be too physically meaningful, so I wouldn't recommend it. So this basically concludes the demo of some of the basic features of the AtomGraph object. I won't take you through every single option in the building. Those are covered pretty well in the docs, how you can customize the different options when the graph is actually built. But I will show one other thing, which is that this constructor broadcasts really nicely. So we can pull every structure from this directory that I have here and build a graph for each one. It handles, for example, the case where I've deliberately thrown in a sort of pathological one here where you get nans in the graph Laplacian, and so it won't build that one. And we can just get a list. If we actually look at what this list of files looks like, you can see that there's multiple different file types, some CIFs, some XYZ files, POSCAR there. So this is very robust. You can have a big mishmash of different sorts of files. It will by default name them just after the file name. You can of course set that yourself as well. And if we now look at, oops, we can look and see. So this one is a methane molecule. You can even visualize that if we want to. Got a nice little pentagram kind of thing look in there. So anyway, this concludes this demo. I will now hand a couple of these graphs off to my wonderful GSOC student, Anant Dajamadam, and he will create some feature descriptors for them and show you how encoding features works. Thanks.
All right, thanks for the introduction, Rachel. Now that we have represented tungsten disulfide using an AtomGraph, the next immediate and intuitive thing to do would be to actually describe the features of the compound itself. For this, we'll see how we can use a feature descriptor, which is the type that describes the features of an atom's object. Let's see how we can describe the elemental features of every atom present in the WS2 AtomGraph that we created earlier. Let's suppose the features of interest to us are atomic mass and the block to which an element belongs. The block feature by default is categorical and is not log-spaced. Atomic mass, on the other hand, is not categorical but is log-spaced. And the element feature descriptor type supports these options for handling different types of data. We can easily create the feature descriptors for these types by simply specifying the feature names like so. For instance, we can just say EFBF block equal to element feature descriptor and the feature name, which is block. We could also specify more options like this. EFB underscore atomic mass is equal to element feature descriptor for the feature atomic mass, and we specify the number of bins as 4 and log space as true. We'll soon see why and how options like n bins and log space are essential. We can also find the output shape, which is essentially the total number of values that a feature can be represented as. For instance, the output shape for feature block would be 4. And this tracks because the values that a block feature can have are S, P, D, and F. But having feature descriptors like this is meaningful only when we have the ability to encode and decode an atom's object using these feature descriptors. The encoding and decoding scheme is determined by an object of type codec, and for element feature descriptor, the default codec is called one hot, one cold. Codecs are characterized by the parameters that the encoding and decoding scheme would use. In case of one hot, one cold, these parameters are if it should be log space or not, and the number of bins. This allows users to create their own custom encoding and decoding functions that are compatible with a feature descriptor, and also enables them to use these custom functions in a plug and play manner with ease. We provide two interfaces which can be used for encoding atoms objects with a feature descriptor. One way we could do it is by calling the function encode, which takes in the feature descriptor object followed by the object Atom's object itself as arguments. The second way, and my personal favorite, is by using the callable nature of an element feature descriptor object itself. You could, for instance, say something like encoded underscore block of features is equal to EFD of WS2, which is your Atoms object. And it would return the encoded value corresponding to the codec scheme attached to the feature descriptor, which in this case is one code attached to the feature descriptor for the block feature. As we established already, there are a couple of ways that we can encode an Atoms object, and there's also a codec specified for each feature descriptor. So there obviously also has to be a well-defined interface for decoding as well, right? Let's try to decode one of the values that we've just encoded. We can do this using the decode method, which in a similar fashion to the encode interface that we saw first, takes the feature descriptor followed by the features that you want to decode. Here we see that we get 2 Ds followed by 4 Ps, which makes sense since tungsten is a D block element and sulfur is a P block element. Now that we've kind of glossed over feature descriptors, how they can be created, encoded, interpreted, and decoded, it's time to see how we can actually use these feature descriptors to define a featurization scheme. Over to you, Rachel.
Thanks, Ananth. So the last thing we need to do is build up a featurization scheme. So there are 2 ways we can construct the featurization that we're going to build, which is a graph node featurization. This simply describes a featurization that assigns features to each node in a graph. So we can do it with a sort of convenience constructor where we simply provide the names like so, and this will construct it using the default parameters. However, if we have some features with a couple of custom aspects to the encoding, such as the ones Ananth built, we can also provide directly those objects that he's built to build a featurization that way. And if we see, we can actually inspect those and see that they look the same as the ones that he built before. So we can then featurize this same graph that we've been playing with for tungsten disulfide. And we do that with this function here, featurize, conveniently enough. And that returns what's called a featurized atoms object, which I've obviously yet to define a pretty printing string for. We can inspect what the result of that featurization was. And it's as we expect. So we see 2 columns, the same here for the tungsten, which is D block, and in the larger atomic mass bin, and then 4 here for the sulfur, which is P block, and in the next smaller atomic mass bin. But we don't have to read that off from these one-hot vectors ourselves. We can use the decode function, and it will actually show us exactly what we have there. So we see these 2D and pretty large bounds on the atomic mass, and then the P block ones with these sort of intermediate bounds in the atomic mass. Recall that those bins, as Ananth built the structure, were logarithmically spaced. So that shows you how we can build, featurize, and encode and decode these different features on some atom graphs. Hopefully gives you a sense for how this package actually works in practice. And thanks so much for paying attention to these demos. So you hopefully now have a sense of how the chemistry featurization package works. I'm going to talk through now a couple of the future plans. Obviously, this is really only in the beginning stages at the moment. So unsurprisingly, we certainly intend to implement some more feature descriptors and featurization schemes. There are a lot of great things out there that have been proposed and shown to work really well, of which we have really only a small fraction implemented at the moment. As I alluded to before, we also really want to emphasize this sort of interoperability between the organic and the sort of molecule focused world and the inorganic and crystal focused worlds. So that's something that we're going to continue to think about and focus on. A lot of this currently relies on PyCall, which is all right for some things, but other things has been causing some headaches. So we eventually want to move towards as much of it as is practical to be implemented in pure Julia. And of course, we'd love to have more contributors. If you're interested, you can check out the issues page where there's a number of ideas for directions that we'd like to go. So with the last couple of minutes that I have, I want to talk a little bit about one of the actual models that the Chemellia ecosystem exports, and that's AtomicGraphNets.jl. So this is an implementation very similar to the CGCNN or crystal graph convolutional neural nets that has a Python implementation currently. So this defines 2 Flux.jl layers, the convolutional layer itself, and then a pooling layer. And it exports some model pre-builders for various standard types of architectures for these sorts of models. And we've shown on a pretty standard and simple benchmarking task, which is formation energy
of all of the stable ordered materials in the materialsproject.org database that we can get comparable or perhaps even slightly better performance in terms of accuracy, and pretty drastically reduce, note the log scale here, training time with our package as compared to the standard Python implementation. So this is, of course, just a small sneak peek. I encourage you to go and play with the things that are out there, and we're actively pushing more stuff most days and certainly every week. So I'll finish up with just a couple of acknowledgements. There's a lot of folks without whose help this work would never have happened. First off, the wonderful Cormelian, who helped with our beautiful logo, Daria Gandhi from Flux for adjoints and other various wizardry that make the models run smoothly. Of course, Anant for his amazing development work that he continues to do throughout the ecosystem. Sakshi, who's a wonderful master's student I've been working with here at CMU, who's been giving feedback on the interface and the docs of the package as she learns how to use them. Sina and Sam from the Mulsi, who were wonderful, wonderful mentors during my tenure as a Mulsi software fellow. And finally, financial support from ARPA-E, Mulsi, and the Google Summer of Code program. Thank you so much for your attention. And I really would be happy to take questions on the Julia Slack or any way that you can figure out to contact me. Thank you so much.